Welcome to the video lecture on right triangle trigonometry. In this lecture, we're going to talk about our 6 trigonometric functions in the context of a right triangle. So let's consider a right triangle with theta as one of the acute angles. So if you look at this picture right here, the way that we would label these sides is the side opposite your right angle is always called your hypotenuse, so that would be the longest side of this right triangle. The side across from or opposite from that angle theta is called the opposite side, and the side that touches the angle theta, one of the legs that makes up that angle theta, is called the adjacent side. So using those labels, we are going to define our 6 trigonometric functions as follows. So sine of theta will be defined to be the opposite side divided by the hypotenuse. Cosine is defined to be adjacent side over hypotenuse. Tangent of theta is defined to be opposite over adjacent. Cosecant of theta is hypotenuse over opposite. Secant of theta is hypotenuse over adjacent. And cotangent of theta is adjacent over opposite. So in this definition, you can see that those reciprocal relationships still are being maintained. If sine is opposite over hypotenuse, cosecant is just the reciprocal of that. Similarly for cosine, secant is the reciprocal of how cosine was defined, and cotangent is the reciprocal of how tangent was defined. So all of those earlier relationships that we've talked about are still being maintained. One way to help you remember how these definitions are created is by this little acronym here, SOHCAHTOA. So S is sine, O is opposite, H is hypotenuse. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So that gives you those top 3 trig functions, and from those 3 you can always get the other 3. So we're going to practice using this. Since any 2 right triangles with an acute angle theta are similar, the ratios are the same regardless of the size of the triangle. So for example, if we take 2 right triangles here, these are similar triangles. Similar triangles occur whenever you have 2 angles that are equal. So both of these have a right angle, and both of them share this angle theta. So that makes them similar. If we take a look at the trig functions, then the way that these would be defined would be sine of theta is going to be the opposite side, which is this 3, over the hypotenuse, which is this 5. Therefore, cosecant of theta is the reciprocal of that, 5 over 3. Cosine of theta is defined to be adjacent, which would be the side touching angle theta, so that would be that 4, over the hypotenuse, which is that 5. And therefore, secant of theta would be the reciprocal, 5/4. And finally, tangent of theta would be opposite, which is 3, over adjacent, which is 4. And notice for tangent, you would get that same ratio if you had taken the sine fraction, 3/5, and divided it by the cosine fraction, 4/5, because the 5s would cancel out. So again, that reciprocal relationship still is being maintained, as well as those earlier definitions for sines, cosines, tangents, etc. And then finally here, cotangent of theta would be the reciprocal of tangent, so 4 over 3. Now if we take a look at this similar triangle, let's find the sine of theta on this triangle, and its opposite side here is 24, and its hypotenuse side is 40. And if you reduce that, both of those are divisible by what? By 8. So if I divide by 8, I'm going to be left with a 3 on top and a 5 on the bottom. So same exact ratio value because we're talking about the same angle. So sine of theta on this triangle should always be the same as the sine of theta on any similar triangle. Similarly here, cosecant of theta would be that reciprocal 40 over 24, which is going to reduce to that 5/3. Cosine of theta would be the adjacent side, which this time around is 32, divided by the hypotenuse side, which is that 40. So if I divide by 8 again, 32 divided by 8 is 4, and 40 divided by 8 is 5. Secant of theta would be the 40 over the 32, which reduces to 5/4. And tangent of theta would be the opposite side, which is the 24, divided by the adjacent side, which is 32, and if I divide by 8, I get 3/4. So cotangent of theta would be 32 over 24, which reduces to 4/3. So because these angle thetas are equal, the sines, cosines, tangents, etc. of those values should be equal regardless of which triangle you're on, and they are, because these fractional ratios do reduce to equivalent values. Okay, let's take a look at this next example. Compute the trigonometric ratios for angles alpha and beta in the following triangle. So let's start with finding all of the trig values for alpha. So if I take a look at sine of alpha, its opposite side would be this 2, and the hypotenuse side would be this 3, the side opposite that right angle. Cosine of alpha would be the adjacent side, which is this leg down here, square root of 5, divided by that hypotenuse 3. Tangent of alpha would be the opposite side, which is 2, divided by the adjacent side, root 5. If I take a look at cotangent of alpha, that would be the reciprocal of tangent, so root 5 over 2. If I take a look at secant of alpha, that would be the reciprocal of this cosine value, so 3 over root 5. And the reciprocal of sine is that cosecant of alpha, so that would become 3/2. Now let's take a look at all of these trig values for the angle beta. So this time let's take a look at sine of beta. So if beta is this angle up here at the top, then now the opposite side in relation to that angle would be the root 5, but the hypotenuse is still this side 3. And the cosine of beta now would be the adjacent side to angle beta, which is now this leg here, 2, over the hypotenuse 3. And if I take a look at the tangent of beta would be its opposite side, which is this root 5, over the 2, the adjacent side. Cotangent of beta would be the adjacent over the hypotenuse, so 2 over root 5. Secant of beta would be the reciprocal of the cosine of beta, so 3/2, and cosecant of beta would be the reciprocal of the sine of beta, so 3 over root 5. Now what you want to notice here is that there is a relationship between some of these sine values and cosine values, etc., comparing alphas and betas. So if you take a look at our two columns here, notice that this 2/3 was sine of alpha, but 2/3 was also cosine of beta. So these two values, sine alpha and cosine beta, turned out to have the same exact ratio. Likewise, cosine of alpha, which was root 5 over 3, has the same ratio as sine of beta. If you look at tangent of alpha, that's 2 over root 5. That's the same as cotangent of beta. And cotangent of alpha, which was root 5 over 2, is the same as tangent of beta. And finally, secant of alpha turns out to be the same as cosecant of beta, and cosecant of alpha is the same as secant of beta. So let's talk about this relationship. First of all, what's the relationship between alpha and beta? What do we know about alpha and beta? Since they are the two acute angles in a right triangle, and the sum of all three angles in a triangle is always 180 degrees, we already know that one of the angles is a 90-degree angle, so that forces these other two angles to have to add up to 90, so we get 180 altogether. So alpha plus beta must equal 90 degrees. If you want to write that in another way and solve this for alpha, we could subtract the beta to the other side, and that means alpha is 90 degrees minus beta. If you're using radians, this could be written as alpha is pi over 2 minus beta, and what that means is that's the definition of what we call complementary angles. Any two angles that add up to 90 degrees are called complementary angles. So this is a theorem that we have called the complementary angle theorem, and this is what it says. Exactly the conclusions that we came up with up here. So sine of alpha, let me actually use theta here to be very general. Sine of any angle theta will be the same as cosine of its complement. So if you're using degrees, then that would be written as cosine of 90 degrees minus theta, or you could write that as sine of theta equals cosine of pi over 2 minus theta. So the sine on one side is equal to the cosine of the complement. So this angle theta and this angle pi over 2 minus theta, those are the complements. Similarly for tangent, we would say that the tangent of any angle theta is equal to the cotangent of its complement. So either 90 minus theta or tangent of theta is equal to cotangent of pi over 2 minus theta if we're using radians. And finally, secant of theta will always equal to the cosecant of its complement. So 90 minus theta or pi over 2 minus theta. So this is called your complementary angle theorem. And another sort of common word that you might hear is this term cofunctions. And what we say is that sine and cosine are cofunctions. Let me write a little bit more neatly here. So these are considered cofunctions. Tangent and cotangent are considered cofunctions, and secant and cosecant are considered cofunctions. And what does this word cofunctions mean? It means exactly this complementary angle theorem up here. So that if you look at sine of an angle, then that will always equal to cosine of its complement. Tangent will equal to the cotangent of the complement angle, and secant will equal to the cosecant of the complement of the angle. So let me show you an example here of how this might be used. If we wanted to find the sine of 35 degrees using the cofunction value, notice that we're in degrees here. So this means that this would have to equal cosine of the complement of 35 degrees. So if we're in degrees, that would be 90 degrees minus 35 degrees. So that's the same as 55 degrees. So sine of 35 degrees has exactly the same value as cosine of 55 degrees. Now if we look at the next example here, this is obviously in radians because we see that pi over 7. So if we're going to use the cofunction for cotangent is tangent, and I want to use pi over 2 minus this pi over 7 to get the complementary angle. And if you get a little common denominator here of 14, this would be 7 pi over 14 is equivalent to pi over 2. And this would be 2 pi over 14 is equivalent to pi over 7. So now that I have that common denominator, I can subtract. 7 pi minus 2 pi makes this 5 pi over 14. So cotangent of pi over 7 has exactly the same value as tangent of 5 pi over 14. And then finally, secant of 25 degrees. To use the cofunction value, we need the cofunction of secant, which is cosecant. We're in degrees, so to get the complementary angle, I want 90 minus 25. And 90 minus 25 is just 65 degrees. So the secant of 25 degrees has exactly the same value as the cosecant of 65 degrees. Now certain right triangles have ratios that can be calculated easily using the Pythagorean theorem, and these ratios lead to confirmation of some of the special values of the trig functions that we have memorized, and these are the ones that are similar to the things we found on our unit circle, like the pi over 6 angles, pi over 4 angles, pi over 3 angles, etc. So let's take a look at just a square that has a side of 1 all the way around. And by using Pythagorean theorem, I can find out the length of this diagonal. It would be 1 squared plus 1 squared, which is just 2, and the square root of that. So this diagonal has to be the square root of 2. So if I wanted to find some trig values here, because this is a 90-degree angle, and we're bisecting it with this diagonal, then this is just a 45-degree angle, and similarly so would this one be as well. So according to our right triangle trig definitions, sine of 45 degrees, if I'm referring to this bottom 45 right here, would be the opposite side, which would be this 1, divided by the hypotenuse of this right triangle, which is this square root of 2 that we just figured out from Pythagorean theorem. And if you rationalize the denominator there, then that just becomes root 2 over 2. Similarly, cosine of 45 degrees would be the adjacent side to this angle, which is this 1 over here, divided by the hypotenuse, which is this root 2, and that's also equal to root 2 over 2. And then finally, tangent of 45 degrees is the opposite side, which is 1, divided by the adjacent side, which is also 1, so we just get 1 back again. So I'm just going to do the major 3 values here, but these are exactly the same 3 values that you should have memorized from your unit circle where you were thinking about 45 degrees as pi over 4. Now let's take a look at an equilateral triangle. So all 3 sides of the triangle are equal, therefore all 3 angles of the triangle must be equal. So that forces this to be 60 degrees, 60 degrees, and up here would be 60 degrees as well, so that they all add up to 180 degrees. And if this is 60 and I drop down a perpendicular that's going to bisect this angle, then each of these would be 30. So we have a 30, 60, 90 right triangle for each half of this picture here. Now let's figure out some of our additional side lengths. Since this whole length down here is 1 and I'm bisecting it with this perpendicular height, then this distance from here to here is just a half. And in order to find this height right here, I could use Pythagorean theorem. So that height squared, which is this leg, plus this leg over here, which is that 1/2 squared, has to equal this hypotenuse squared, which is 1. So we get h squared plus 1/4 is equal to 1. When I subtract 1 minus 1/4, I get 3/4. And when I take a square root of both sides, I'm only going to take the positive value because we're talking about distances. This becomes square root of 3 over 2. So now knowing that, I can use my trig ratios to figure out what sine of 60 degrees is. Here's 60 degrees down here. It would be the opposite side, which is this root 3 over 2, divided by the hypotenuse, which is 1. So that's just square root of 3 over 2. Cosine of 60 degrees would be the adjacent side, which is this 1/2, divided by the hypotenuse, which is 1. So that's equal to 1/2 still. And tangent of 60 degrees would be the opposite side, which is root 3 over 2, divided by the adjacent side, which is 1/2, and these 2's are going to cancel each other out, so we just get a root 3. Now let's take a look at the 30-degree angle. So let's find sine of 30 degrees. So now we're up here, and the opposite side would be this 1/2 over the hypotenuse, which is still 1. So now we get 1/2. Cosine of 30 degrees would be this adjacent side, root 3 over 2, divided by the hypotenuse 1, so still square root of 3 over 2, and tangent of 30 degrees would be the opposite side, which is this 1/2, divided by the adjacent side, which is this root 3 over 2. The 2's cancel, and we get 1 over root 3, and if you rationalize the denominator, that's the same as square root of 3 over 3. So 60 degrees is the same as pi over 3, 30 degrees is the same as pi over 6, and this 45 degrees was the same as pi over 4. So for the pi over 3 angles, we got that the sine was root 3 over 2, the cosine was 1/2 and the tangent was √3. And for the pi/6 angles, sine was 1/2, cosine was √3/2, and tangent was √3/3. And again, those all match exactly the same values that we have memorized from our unit circle. So even though we're defining our trig functions using right triangles instead of a unit circle, the same exact values are recurring, which is a good thing. We don't want to have the sine values be something using right triangles, but being something totally different on a unit circle. We want them to be consistent, and they are. We've just shown that they are. So these are all of our common angles in degrees and radians, and these are all of the common memorized values that you need to know by heart for all 6 trig functions. And these are consistent whether you do them using right triangles or whether you do them using the unit circle. So no matter which way you think about it, you'll be getting the same exact values either way. So have this chart memorized. Now, to find the values of the trigonometric ratios for other angles, the ones that aren't on that chart, then we have to use our calculator and some numerical methods that are programmed into these calculators. We're going to follow the convention that if there are no units written on the measure of an angle, then we're going to assume that it's in radians. If we want the measure of an angle to be in degrees, then you have to see that little degree symbol. So for example, if the problem said, find the sine of 1 radian, then you would just write that sine of 1. You wouldn't see any units at all. And when you do that on your calculator, you end up getting 0.84147. If I wanted to find the sine of 1 degree, then you should see that little degree symbol after the 1, and it has a totally different value, 0.0175. So let's practice finding these on our calculator. So if I want cosine of 32 degrees, first you need to make sure that you are in degree mode on your calculator. So let's pull up the calculator. To make sure or find out what mode you're in, just press mode. It usually defaults to radian mode, but I want to be in degrees. So I'm going to need to arrow over to degree and hit enter so that it gets highlighted. And now quit and go back to your home screen. And I'm just going to find cosine of 32. Notice I don't see a degree symbol up here, but you need to remember we were just in degree mode, so it's going to assume degrees, and we get 0.8480. Okay, now if I want tangent of 0.5 or secant of 0.1, both of those do not have the degree symbol, so we want to be back in radians. So I'm going to go back to mode, and I'm going to switch it back to radians by highlighting it. And then the first one here was tangent, so I'm going to do tangent of 0.5. We were in radians now, so the calculator knows that, and this is 0.5463. Approximately. These are all approximate values, and we're rounding off to about 4 decimal places. Now to find secant of 0.1, there's no secant button on your calculator, so this is where those reciprocal properties come into play. Secant is the same as the reciprocal of cosine, so I need to do 1 over cosine of 0.1 and type that into my calculator. So we're going to do 1 divided by, 1 divided by cosine of 0.1. We're still in radians, and we get 1.0050. And again, that's just an approximate value. Now what we're going to move into next is solving triangles. Many applied problems in navigation, surveying, astronomy, and measuring distances can be used using right triangles and the trigonometric ratios. So to solve a triangle means to find all 6 component parts of the triangle. So finding all 3 sides and all 3 angles from the information given about the triangle. So on this example right here, we're given this triangle ABC. We know this right angle C, and we know this acute angle A is 30 degrees. So there's still one more angle up here that we need to know. And that should be relatively easy to find because you know that the sum of all three angles in any triangle always has to add up to 180 degrees. And if it's a right triangle, then the two acute angles always have to add to 90. So if angle A is 30, that forces angle B to be 60 degrees. So there's all three angles. We know all three already. The only one we actually had to solve for was angle B. Now we need to find all three sides. The only side I know here is this hypotenuse, so I need to find the two legs. And that's where our trig ratios come into play. Since I can't use Pythagorean theorem yet, since there's only one known value, one known side, we're going to have to set up a correct trig function, trig ratio, to represent something that we could solve. Now there's many choices here for how you do this. Suppose you wanted to start with this angle 30 degrees. You could use sines or you could use cosines. It's totally up to you. You probably wouldn't want to use tangents because tangent would require the opposite and the adjacent side, and I don't know either one of those. But I do know the hypotenuse. So we'd want to use something that refers to the hypotenuse, which is why I'm suggesting either sine or cosine. So let's try sine of 30 degrees. According to our definition, that's the opposite side, which we are calling A, over the hypotenuse, which is 12. Now on this particular example, you are given a very nice angle, sine of 30 degrees. This is one that I would expect you to have memorized. That's the same as pi over 6. So what's the sine of pi over 6? It's equal to a half. You need to have that memorized. So this just becomes 1/2 is equal to a over 12, and to solve that for a, I'm just going to multiply both sides by that 12. 1/2 of 12 gives me 6. So we now know that side A is equal to 6. We still need side B, so you have options here. You could use Pythagorean theorem, that's perfectly fine, and you could do b squared plus 6 squared is equal to 12 squared and solve that. That works. Another option is you could use those trig ratios again. Instead of using sine of 30 degrees, we could do cosine of 30 degrees because that uses the adjacent side, which is what we're calling B, and it uses the hypotenuse, which we know is 12. Other options, you could have used the 60-degree angle and done a sine for that, or you could have done a tangent of either angle and used the 6 that you had for A and the B that you're looking for. So there's lots of ways to do these problems. Now cosine of 30 degrees, again, that's that pi over 6. So cosine of a pi over 6, you have to have memorized that that's square root of 3 over 2. So this becomes square root of 3 over 2 equals b over 12. Again, I'm going to just multiply both sides by 12. 2 goes into 12 6 times, so we're left with 6 root 3 is equal to b. So we just found the three things that we had unknown in the problem. We already knew the other two angles and the third side. So this would be my final answer. Okay, let's try that again for the next example. So this time we are given the right angle over here and we're given this angle is 45 degrees. That again forces us to know what this third angle must be. This angle here must also be 45 degrees because these two have to add up to 90. Now, if you know a little bit about geometry, you know that that forces this to be a 45-45 right triangle. It also makes it isosceles because you have two base angles here that are equal. So you can use that fact to help you out here. If you know that this leg is 12, then that forces this leg to be 12 as well because they are across from equal angles. So these two sides have to be the same. If you didn't know that, then you could certainly use your trig functions to figure it out. Okay? Let's show how to do that. So suppose that I started with this 45-degree angle here, and you could use either one. I'm just going to use the one on the left. Then say I wanted to find out what y was, I could use a tangent. I could say tangent of 45 degrees is the opposite side, which is this y that we were looking for, over the adjacent side, which is this leg over here, which we already know is 12. Tangent of 45 degrees is the tangent of pi over 4. Sine and cosine of pi over 4 are equal, so when you divide them to get your tangent, this is just going to become a 1. And you need to have that memorized. So that's why when I solve this for y and multiply both sides by 12, we just get y is equal to 12. So you can do it the long way using this trig function, or you could just recognize that these have to be equal sides since they're across from equal angles. Now we still need to know what x is, so again you have choices here. You could use Pythagorean theorem. You could say 12 squared plus 12 squared has to equal x squared, and then solve for x. That works. Another option is to use a different trig function. So I could use, say, a cosine. Cosine of 45 degrees, again using this bottom left 45-degree angle, is supposed to be the adjacent side, which is this 12 over here, over the hypotenuse, which is this side x, because that's across from the 90. Now what's the cosine of 45 degrees? That's the same as cosine of pi over 4, and all the pi over 4 angles have cosine and sine both equaling root 2 over 2. Now how do I solve this equation for x? An easy way to do it is just to multiply across. This is a proportion, so you can multiply across the diagonals. The other option is just to think of multiplying both sides by 2x, and that's going to give you the same exact answer. So if you multiply both sides by that common denominator underneath. If you do that, the 2's would cancel, and you'd get root 2 times x, which is exactly what this diagonal is here. And on the other side, the x's would cancel, and you'd get 12 times 2, which is 24, which is just this diagonal going this direction. And now to finish solving for x, divide both sides by square root of 2. I'm going to go ahead and rationalize that. So I'm going to multiply by root 2 over 2. That would give me 24 square root of 2 over 2, and 2 reduces on the outside and turns this into a 12 root 2. So my hypotenuse must be 12 root 2. Okay? Now on the next example here, again we want to do the same thing. I have my right angle and I have one acute angle given to me, 22 degrees, but I still need to find my other angle over here, and this angle has to be the complement of 22 degrees because these two have to add up to 90. So 90 degrees minus 22 degrees would be 68 degrees. So this has to be a 68-degree angle. So now we know all three angles. We still need to find our other two sides, or two legs. We know the hypotenuse. So I'm going to use sines and cosines again. So I'm going to do, let's try cosine of 68 degrees. Again, you could use the 22 if you prefer. It's totally up to you. According to definition of cosine, that's the adjacent side, which is our x, over the hypotenuse, which we know is 1,000. Now to solve this for x, we would want to multiply both sides by 1,000. Now 68 degrees is not one of our common angles, so you're going to have to use a calculator to figure out what this value is on the left-hand side. And we want to be in degree mode because this is 68 degrees. So let's pull up the calculator. I'm going to need to switch my mode back to degrees. And we wanted 1,000 times cosine of 68. And that gives me 374.61. I'll round off to 2 decimal places here. So x is 374.61 approximately. Now we're going to do that all over again, but this time we're going to do it for y to find y. And in order to use that 68-degree angle again, y is opposited, so I'm going to need something that refers to the opposite side and that hypotenuse 1,000, so we need a sine. So sine of 68 degrees would be the opposite side y over the hypotenuse, which is 1,000, and if I multiply that 1,000 on both sides, then we're looking for whatever 1,000 times sine of 68 is? So we get 927.18. Okay, so if the angles are not ones that are common, like our 30 degrees, 60 degrees, or 45 degrees, or various quadrant versions of those, then you will have to pull out the calculator to finish solving the problem. Okay, in the last few examples, it was fairly easy to figure out what the missing third angle was because we already knew the other two. But sometimes we will need to find an angle of a triangle if the sides are known, such as sine of theta is equal to a half. In this case, clearly theta would need to be either 30 degrees or 120 degrees because that's where sine of that angle is equal to positive 1/2. But if we know that we have a right triangle, theta can't be greater than 90 degrees. So in that case, the theta would have to be 30 degrees. Sometimes, however, you might have something like you know that sine of alpha is equal to 4/5. This is not a value that we have memorized. It's not like one of our root 3 over 2's or root 2 over 2's. So we would need to use a calculator to sort of undo this trigonometric function, to undo this sine, so we could figure out what the alpha is. And in order to do that, you use the inverse sine button on your calculator. On some sort of older calculators, you might see it written this way, INVSIN. But on most calculators these days, it's going to look like a sign with a little -1, which stands for inverse function. So this is the inverse sine button, and that's what you would use to undo the sine function. So to find alpha using the calculator, you would just enter in inverse sine of 4/5 or 2/3 or whatever the fraction happened to be, and that would give you your angle theta. Now you have to remember what mode you're in because the answer that you get is going to be in degrees if you're in degree mode, and the answer that you get for theta will be in radians if you're in radian mode. So let's try some examples like this. Here is a problem where we only know the 90-degree angle. We don't know either of the two acute angles, so it's not easy to tell what they should be. However, we do have two sides given to us. So what we want to figure out in order to solve this triangle is we're going to need to figure out the third side and the other two missing angles. So which of these three things that are unknown to us could we easily figure out right away? The third side, this side A, because if you know two sides of a right triangle, you can always use Pythagorean theorem to find the third side. So according to Pythagorean theorem, a squared plus 5 squared would have to equal the Pythagorean, or the hypotenuse squared. So if we solve this, we're going to get a squared plus 25 equals 169. And if I subtract 25 from both sides, we get 144. And if I take a square root of both sides, that's going to give me positive 12. So we know that the missing third side must be 12. Okay? So now we know all three sides. How can we use that to help us find our two acute angles? Because it's a right triangle, we can use right triangle trigonometry to help us set up some trig ratios that we can solve. So let's say I wanted to find alpha first. You have some choices here. You could use a cosine of alpha, which would use the adjacent side 5 and the hypotenuse 13. So that would tell you that cosine of alpha has to equal the adjacent side 5 divided by the hypotenuse 13. Another option is you could use sine. You could say sine of alpha is equal to 12 over 13, and it's going to give you the same exact angle because those are those cofunctions again. So let's see about how to solve this for alpha. If we want to get alpha by itself, then we need to undo the cosine, which is exactly what that inverse cosine function is for. So alpha will be the inverse cosine of this fraction 5/13. Now if you go to your calculator and type that in, to get inverse cosine you need to use this little blue cosine with a -1. So you have to do second cosine, and you'll see that little -1 pop up, and we want 5 divided by 13, and if I hit enter, we get 67.38. Now the question is this in radians or is this in degrees? It depends on which mode we are in. So let me check my mode. We're in degree mode. So this is the angle alpha in degrees. So 67.4 degrees. I'll round it off. So alpha is approximately 67.4 degrees. Now to get beta, you have choices. If you know this acute angle is 67.4, then this angle beta would have to be 90 minus that. So that would be one quick, easy way to get beta. The other option is you could use another trig function. So you could say cosine of beta is equal to the adjacent side 12 over the hypotenuse 13, or you could have said sine of alpha is, sine of beta is 5 over 13. You could have used a tangent, lots of different options here. So if I finished off this equation that I have written here, then to find beta I have to undo this cosine again. So inverse cosine of 12/13 on my calculator, do second cosine 12 divided by 13. We're still in degree mode, so we get 22.6. And that's exactly what you would get if you subtracted 90 minus 67.4. So you have lots and lots of choices for how to find these values. So we found alpha was 67.4 degrees, beta was 22.6 degrees, and we knew that side A was 12. Okay, so let's take a look at some common types of applications that you'll see. In the next several examples, we're going to talk about something called an angle of elevation and an angle of depression. Now, an angle of elevation is defined to be the angle between the line of sight and the horizontal. So if you imagine this person looking off into the distance, looking straight ahead, parallel to the ground, would be that horizontal line of sight. And then looking up to whatever object you're trying to look at would be your line of sight, and the angle between that line of sight and the horizontal is this angle theta, which is what we're calling the angle of elevation. When you have to look up to something, then that's an angle of elevation. Now an angle of depression is almost identical to that, but this time you're usually standing up above and looking down at some object. So your horizontal parallel to the ground would be up here, and then I have to look down to that direct line of sight, and that downward angle is called your angle of depression. So let's see a couple of examples using these ideas. Suppose that we have a plane flying at 35,000 feet, and it estimates the angle of depression to a point on the ground at the base of a physical structure to be 22 degrees. What is the distance between the plane and the base of the physical structure? So drawing a picture is absolutely key for these problems. First of all, we have a plane, and then we have this angle of depression to a point on the ground at the base of a physical structure. So over here off in the distance is my physical structure, and we're looking at the base of that physical structure. So we're looking down here. So from the plane to that base of that structure, draw that diagonal line of sight. So there's my line of sight. If the plane were to continue flying horizontal, then this would be that horizontal direction. The angle from that horizontal down to that diagonal line of sight, that's this angle of depression, so that's 22 degrees. We also know that the plane is flying at a height of 35,000 feet, so it is perpendicular. If I draw that perpendicular down, this height here is 35,000 feet. That perpendicular is making a right angle to the ground, so we're kind of dealing with a right triangle right here. Now notice that this angle here is 22 degrees. and that's not one of the angles inside of my right triangle. So you have a couple choices here. You could use the complementary angle theorem and figure out this one, which would have to be 90 minus 22 because the two together are forming a 90-degree angle. Or you can use a little bit of geometry. Here's a horizontal, and you have this transversal cutting through those two parallel lines. What it creates are what are called alternate interior angles, and there's a theorem in geometry that says this interior angle must be congruent to this interior angle on the other side. I like to use this theorem a lot, and that way it tells me that this bottom acute angle must be 22 degrees. So these are called alternate interior angles. Because of that 22 degrees, again, you could find this one up here. These two have to add up to 90 degrees, so you could easily figure out this top angle. It's not important in terms of the problem because we have enough information to be able to answer the question. So usually I only figure out what I absolutely need to in order to solve the problem. Now, what is it we're trying to solve for? We want to know the distance between the plane and the base of the structure. So here's the plane. Here's the base of the structure down here. So the quickest distance between them would be this hypotenuse over here. So we're looking to find this hypotenuse, so I'm going to call that x. All right, take a look at our picture. If I'm using this 22 degrees, what sides do I know in relation to that 22 degrees? I know that I have the opposite side, which is this 35,000, and we're looking to find this hypotenuse x. So which trig function deals with opposite and hypotenuse? Well, that would be sine. So according to my right triangle trig, and I'm using right triangle trig because I have a right triangle, I have this right angle, sine of 22 degrees is equal to the opposite side, which is this 35,000, divided by the hypotenuse, which is our x. Now, in order to solve this, first thing I would do is get rid of that fraction by multiplying x on both sides. 22 degrees is not one of our nice angles, so we are going to have to use our calculator for this. I'm going to wait and figure that out until the very last moment. So I'm going to try to solve this completely for x first and then pull out the calculator. So if I wanted to solve this for x, I would want to divide both sides by that sine of 22 degrees. So the exact value of x will be 35,000 divided by sine of 22. And now is when I would pull out my calculator. I think we are still in degree mode. Yes, we are. You want to double check that. And we wanted 35,000 divided by sine of 22. So we get 93,431.35. So x is approximately 93,431.35. Since the unit on this height here was feet, then the unit on my distance should be feet as well. And that was all that this question was asking for. So there are other sides and angles you could figure out, but they're not important in the problem. So just find what you absolutely need to. Okay, let's take a look at another example. A 600-foot guy wire is attached to the top of a communication tower. If the wire makes an angle of 65 degrees with the ground, how tall is the tower? So let's draw our tower. Now usually these towers are pretty tall and they need some support. So that's what a guy wire is. A guy wire is just a wire that anchors the tower to the ground to help give it some stability, especially when the wind is blowing. And this guy wire is attached to the top of the communication tower. So up here you have this wire going down to the ground level. So there's my wire. It's a 600-foot wire. So this length I know is 600 feet. We're going to assume that our tower is perpendicular to the ground, and we know that the wire right here makes an angle of 65 degrees with the ground. So that has to be this angle right here. So there's my picture. What do I want to know? I want to know how tall is the tower, so I want to know this length right here, this distance, so let's call that our x. So now if you look at this picture, we have this acute angle 65 degrees. It's part of a right triangle. We want to find the opposite side x, and we know the hypotenuse 600. So which trig function uses opposite and hypotenuse? It's that sine again. So we want sine of 65 degrees equals the opposite side, which is our x, over our hypotenuse, which is that 600. To solve for x, we're just going to multiply both sides by 600. So x will be 600 times sine of 65 degrees. Pull out our calculator. Whoops, one too many zeros there again. And we get 543.78. And again, this would be feet because our length of our guy wire was also in feet. So the height of our tower is 543.78 feet. Okay, one more example here. A plane is flying at an elevation of 6,000 feet directly above a straight highway. Two motorists are driving cars on the highway on opposite sides of the plane, and the angle of depression to one car is 40 degrees and to the other car is 65 degrees. How far apart are the cars? So again, the picture here is absolutely key. We have our plane. It's 6,000 feet above the ground, above this highway, if you will. Let me draw my little road. And then we have two cars on opposite sides of the plane. So there's one car over here, and then there's one car on this side. And the angle of depression to one car is 40 degrees, and to the other car is 65. So we need to make sure that we label these angle of depressions correctly. So let's say that we wanted to find the angle of depression to this car over here. Here's the horizontal to the plane. If it were to continue flying in this direction, that would be its horizontal. Its line of sight, direct line of sight to the car, would be this diagonal. And your angle of depression is from the horizontal down to that line of sight. So this would be that 40 degrees. If we go in the other direction, here's the horizontal, here's the direct line of sight, and the angle down from the horizontal to the car is that angle of depression, so this would be that 65 degrees. If you want to use those alternate interior angles, you can. If this one is 65, then that's equivalent to this angle down here, and if this upper angle here is 40, then this lower angle here is also 40. You could also have found these angles up here using 90 minus 40 and 90 minus 65. Either way is perfectly fine. Now what do we want to know? We want to know how far apart are the cars. So we want to know this whole distance across. But you probably can't find that directly because we want to be thinking about these as right triangles. Here's a right angle and here's a right angle. And if we work just within this right angle, I know this angle is 65, I know its opposite side is 6,000, and from that I could probably figure out what this length over here, this adjacent side is. So let's call just this adjacent side right here x. And according to my trig ratio, which one do I need to use if I have an opposite and I want an adjacent? Well, we'd need tangent. So we could do tangent of 65 degrees equals the opposite side, which is that 6,000, over the adjacent side, which is our x. To solve for x, multiply by it on both sides to get it out of that denominator. And then to solve for x here, we'd need to divide both sides by tangent of 65 degrees. Now, we can get a decimal for that, but I'm going to hold off for a moment because that's not the full distance between the two cars. That's just from this car to that perpendicular. We still need to find this distance over here. So let's call that y. And now we can refer to this right triangle on the right side. Using this angle 40 degrees, we know an opposite side, which is 600, and we're looking for an adjacent side, which is that y. So again, I'm going to use tangent as well. So this time, tangent of 40 degrees is the opposite, which is that 6,000, over the adjacent, which is our y. Multiply both sides by y, and then divide both sides by tangent of 40. So y is going to be 6,000 divided by tangent of 40 degrees. What are we looking for? How far apart are the two cars? So we want this whole distance plus this whole distance. So we're trying to figure out what x plus y is. So we need to know what 6,000 divided by tangent of 65 degrees plus 6,000 divided by tangent of 40 degrees is. So I'm just going to type all of this into my calculator and get an approximation. So I want 6,000 divided by tangent of 65 plus 6,000 divided by tangent of 40. And we're still in degree mode. So we get 9,948.37. And this would be feet. So there's our approximate distance between the two cars. Okay? One more example here. Let's find the value of x in the following triangle. So here we have this big triangle. It's really a right triangle because we do have a right angle right here. We know this upper angle is 30 degrees. So just based on that, what must this lower angle down here be? It has to be 60 degrees. Okay, so if that's 60 degrees, you could also figure out a few other angles if you really wanted to. This would have to be 90 because it's forming that sort of perpendicular bisector. So you have a 90-degree angle here. This is 60, so this little piece here must be 30. And since this angle plus this one equal this 90-degree angle, then this one up here must be 60. So we've got lots of little 30 and 60-degree angles going on. Now we want to find out what x is. So what I'm going to do is try to figure out how I can find this x the most efficiently as possible. I'm just going to focus in on this little triangle right here, and it is a right triangle because we have this right angle in the corner, or up here from that perpendicular bisector. We found out that lower bottom corner is 60 degrees, and that forces this one to be 30 degrees. We know this, which is the same as that perpendicular bisector, was 5, and we're looking for x. So if we have this right triangle, how could we figure out what x is? Well, let's use a couple of trig functions, or a trig function here. You could use sines, you could use cosines, whatever you like. I'm going to just go ahead and try a cosine of 30 degrees. You could also try to do something with that 60 degrees and maybe use a sine if you want. But cosine of 30 degrees would use the adjacent side, which is this 5, over the hypotenuse, which is the side opposite that 90-degree angle, which is our x. So that's why this would work. Now 30 degrees, that's one of our good angles. That's the same as pi over 6. So what's cosine of 30 degrees the same as? It's the same as cosine of pi over 6, which is root 3 over 2. So you don't need a calculator for this. You can figure it out in your head. And now how do we solve this for x? Well, my two denominators are 2 and x, so let's multiply both sides by 2x. The 2's cancel on the left side, giving me x root 3. The x's cancel on the right side, giving me 5 times 2 or 10. And if I divide both sides by root 3, we get x equals 10 over root 3. If you rationalize that, that becomes 10 squared root of 3 over 3. So both answers are fine with me. I don't really care so much if you rationalize your denominator or not, but some instructors do require it. Okay, we've talked a lot today about our right triangle definitions of our trig functions. So what we're going to finish up with on the next several examples is tying these right triangle definitions into some earlier problems that we did using a unit circle and showing you that they really are equivalent. So what we're going to take a look at this next example is finding the value of each of the trigonometric functions of alpha if alpha is in standard position and 3, 7 is on the terminal side of angle alpha. So what does all of that mean? Well, first of all, let's draw a little coordinate system and let's plot the point 3, 7. So it's right here, and if we draw this ray going out and drop a perpendicular going down, we're going to create for ourselves a little right triangle. We know this side must be 3 and this side going up must be 7. And remember here we're in quadrant 1 because 3, 7 is in quadrant 1. That's going to be important when we're trying to figure out what signs, either positives or negatives, we want to use on our trig functions. Now, if it says that this angle alpha has terminal side through 3, 7, that just means that this little angle right here is our alpha. So we have a right triangle, and we're trying to find the value of each of the trigonometric functions of alpha. So what that's asking us to find is what is sine of alpha, what is cosine of alpha, what is tangent of alpha, and then the reciprocals, cosecant, secant, and cotangent. So these are problems that we've done previously in our unit circle lecture. So how can we do this thinking in terms of right triangles? Well, we've drawn a right triangle. So if I wanted to know what sine of alpha was using our right triangle definitions, it would be opposite, which is 7, over hypotenuse, which currently I don't know. So we are going to need to figure out what that hypotenuse is. But since I know the two legs, we can use Pythagorean theorem to figure it out. So leg squared, 3 squared, plus the other leg squared, 7 squared, has to equal that hypotenuse squared. 3 squared is 9, 7 squared is 49. When I add those, I get 58. And when I take a square root of both sides, that tells me that this hypotenuse is square root of 58. So now I can use my trig definitions, using those right triangle definitions for our trig functions. Sine should be opposite, which is 7, over hypotenuse, which is square root of 58. I'm not going to bother to rationalize that. I'm just going to leave it like that. If we know sine of alpha, then we know cosecant. Just flip it over. Root 58 over 7. Now cosine of alpha would be adjacent, which is 3, over hypotenuse. So square root of 58. And then the reciprocal of that is just secant. And finally, tangent of alpha becomes opposite over adjacent, so 7 over 3, and cotangent becomes the reciprocal, 3 over 7. And just a quick check, this was in quadrant 1, so everything in quadrant 1 is always positive. So I'm getting all positive values for these 6 trig functions. So everything looks good, and this would be my final answer. Okay, we're going to do something very similar to that. This time, however, we're trying to find the value of each of the trigonometric functions of beta if beta is in standard position and negative 2, 5 is on the terminal side of angle beta. So this time, when we draw our point, negative 2, 5 puts us over here in quadrant 2. So we want to keep that in mind. And I'm going to draw that ray to the origin, and I'm going to drop down a perpendicular, and I'm going to create for myself a little right triangle. So we're forcing this to be a right triangle so we can use those right triangle definitions. This distance here is actually a -2 because we're going to the left, and here we're going up 5, so it's positive. And we're probably going to need to know what that hypotenuse is. So it's going to be that -2 squared, which is 4, plus that 5 squared, which is 25, and that's going to give me a 29. So my hypotenuse must be square root of 29. Now technically, this is a slight issue here, but I want you to notice it. Technically, angle beta is from the positive x-axis to this terminal side over here. So this is actually our angle beta. But when we talked about unit circles, we talked about reference angles. And the reference angle here would be the angle that's closest to the x-axis from that ray, that terminal side ray. So here's my terminal side, this little diagonal right here, and my closest part of the x-axis would be the negative x-axis. So the angle between those two would be right here, and that's actually our reference angle, or beta bar, with that little line over it. So that's going to be my reference angle. And what we know about beta and beta bar, or beta bar, is that these are actually going to have the same angle except for possibly pluses and minuses. And since we're in quadrant 2, we want to keep in mind which trig functions are positive and negative in quadrant 2. And we'll think about that at the end when we're checking our answer. So beta and beta bar, they're not technically the same exact angle, but we're going to use them sort of as thinking of them as the same angle because they're going to really give us the same trig values except for pluses and minuses. So let's make a list of what we need to figure out. We're supposed to find the 6 trig functions of our angle beta. So I would want sine of beta, cosine of beta, tangent of beta, cosecant of beta, secant of beta, and cotangent of beta. Now in quadrant 2, sine is positive. So sine of beta and sine of beta bar should be the same thing. In quadrant 2, cosine is supposed to be negative. So cosine of beta bar, we would want to take its opposite to get cosine of beta. So this answer for cosine beta should be something negative. In quadrant 2, tangent is also negative. So this is going to be the opposite of whatever tangent of beta bar would be. So that's going to be a negative answer. Similarly, cotangent should be negative in quadrant 2. So that's going to be negative. Secant is the same as cosine in terms of sines. So if cosine was negative, so should secant. So this will be negative secant of beta bar. So that should be a negative answer. And in quadrant 2, if sine is positive, then so is cosecant. So these will be the same. So this will be plus, and all the rest will be minus. So that's what I mean by the signs making the only difference. Now how do we figure out what the actual answers are here? We use those right triangle definitions. So what would sine of beta bar be? It would be the opposite side to beta bar, which would be this 5, over the hypotenuse, which is the square root of 29. So cosecant would be square root of 29 over 5. What would cosine of beta bar be? Well, it would be the adjacent side over the hypotenuse. Now, I am using my minus out here instead of thinking of this as a sort of a -2. I don't want to use that negative twice because then they'll cancel out. So if we just think of this as a positive distance of 2 over that hypotenuse square root of 29, and then make the whole fraction negative because we know we're in quadrant 2, that'll keep my signs correct. So the secant would be also negative, but the reciprocal would turn into square root of 29 over 2. Tangent of beta would be opposite over adjacent, so 5 over 2, but in quadrant 2 that's supposed to be negative, and the reciprocal would be -2/5. So it's a little tricky with the signs. I'm going to show you in the next example how I sort of ignore the signs until the very end and not worry about positive and negative distances and so forth to help make it a little bit easier. So let's try one more example. Find the value of the other trigonometric functions if sine of theta is equal to negative 2/3 and theta is in quadrant 3. Okay, so here's how I like to simplify matters to avoid having all these negatives hanging around. I like to just draw a regular right triangle going up like this, thinking about it even if you want in quadrant 2, if you want to, or excuse me, in quadrant 1, if you want to think of it as associated with some axes, you certainly can. But I usually don't even draw in any axes. I just draw myself a nice little right triangle with that acute angle being our theta that we're referring to here. And if I know that sine of theta is equal to negative 2/3, according to our definition of sine, sine is supposed to be opposite over hypotenuse. Now I am going to ignore the negative temporarily. So I am going to let my opposite side to this angle theta, which would be this side over here, be just the 2. And I'm going to let my hypotenuse be the 3. So we're ignoring the signs right now. Now if I know those two sides, what would have to be the third side of this triangle? Well, if we call it x, then Pythagorean theorem says x squared plus 2 squared has to equal 3 squared. So x squared plus 4 equals to 9. So x squared equals to 5. So that missing third side must be square root of 5. Everything here I'm thinking in terms of positives. So let's make our little list. We're trying to find all of these trig functions. We already know what the sine is, but we also want cosine, tangent, cosecant, secant, and cotangent. Now if we know sine, then we know cosecant. That one's easy. To find cosine, we would go to our triangle over here and use our definition. It's adjacent over hypotenuse. So the adjacent side here would be root 5. The hypotenuse side would be the 3. And the secant would be the reciprocal of that. Now I'm not done here. I may come back and adjust the signs on these, but for now let's just figure out what the fraction should be. What about tangent? What would tangent's fraction be? It would be opposite over adjacent. So the 2 over the root 5. So that makes cotangent equal to root 5 over 2. So what I like to do is just draw myself a very simple right triangle, sort of thinking of it as being in quadrant 1, find out all 6 of my fractions, and then I go back in and I use the fact that theta is in quadrant 3. So in quadrant 3, what is supposed to be negative? Everything is negative in quadrant 3 except tangents and cotangents. So the sines and the cosecants should be negative, the cosines and the secants should be negative, but the tangents and cotangents will become positive. And that's my final answer. So it's a nice simple way to kind of ignore the positives and negatives temporarily, ignore the quadrant that you're in temporarily, find out what all of your fractions are, and then put in the correct positives and negatives at the very last step. Okay, next example here. Express tangent of theta in terms of sine of theta, where theta is in quadrant 2. So we want to figure out what tangent of theta is in terms of just the sine function. So here's tangent of theta. Now this doesn't give us any numbers at all. There's no triangle that we're going to draw or anything like that. This is referring to some of those identities that we've talked about in the past. You have to remember that tangent of theta is defined multiple ways. It's defined to be opposite over adjacent, but if we want to think of it in terms of sine, then you need to recall the definition that tangent of theta is the same as sine of theta divided by cosine of theta. Now, the numerator is already in terms of sine. However, the denominator is not. So what we're going to have to do to finish this problem is somehow figure out a way of converting cosine into the sine function. And again, this uses those identities. What's the basic relationship between sine and cosine? It's a very important Pythagorean identity based on that unit circle definition, which says that sine squared of theta plus cosine squared of theta always has to equal 1. And that comes from that unit circle because it's a circle of radius 1. The sine is the y, the cosine is the x, so this is just the equation of that circle, x squared plus y squared equals to 1. Now what I want to do is I want to figure out how to solve this for cosine. So I am going to subtract the sine squared over to the right side, and I'm trying to solve this for cosine, not cosine squared. So to finish it, I'm going to have to take a square root of both sides. Now normally when you take a square root, it's either a plus or a minus. But what quadrant are we in? That's going to determine which of these two signs we use. In quadrant 2, which is where our theta is, cosine of theta should be negative. In quadrant 2, cosines are negatives. So I don't want to use the plus case, I want to use the minus. So now that we know how to rewrite cosine in terms of sine, I'm going to take all of this and replace it for this cosine right here. So here's what tangent becomes. Tangent of theta, which was sine of theta over cosine theta, becomes sine of theta over negative square root of 1 minus sine squared theta. And if you look at what we ended up with here, we now have a formula for what tangent is, and the only things that I see on this side are sines. That's what it means to write tangent in terms of sine only. So that would be our final answer. Alright, that concludes our lecture on right triangle trigonometry. Good luck.